Methane and oxygen react in the presence of a catalyst to form formaldehyde. In a parallel reaction, methane is oxidized to carbon dioxide and water. The feed to the reactor contains equimolar amounts of methane and oxygen. Assume a basis of 100 mole feeds per second. Draw and label a flowchart. Use a degree of freedom analysis based on the extensive reactions to determine how many process variable values must be specified for the remaining variable values to be calculated.
Okay, so now that we have the balance equations for the reactions that take place in this process, and we have also sketched the diagram of the process, we move to the degrees of freedom analysis. Remember that our equation for degrees of freedom analysis is just the number of unknowns minus the number of independent equations. So in this process, the unknowns are in red, and they are molar flow rates, N1, N2, N3, N4, and N5, right here. And also the extent of the two reactions that we have up here. So each one of these reactions is going to have an extent that doesn't quite look like that, but that's the best I can do right now. So we have 1, 2, 3, 4, 5, 6, 7 unknowns. And we subtract the number of independent equations. In this case, 5, 1, 2, 3, 4, 5. So we can work with those 5. So our degrees of freedom analysis is going to be, for the degrees of freedom, 7 minus 5, that is equal to 2. Okay, so now we have to derive expressions for the product stream component flow rates in terms of the two extents of reactions. And how are we going to do that? We're going to use this equation. Here we have the initial number of moles fed, the stoichiometric coefficient of the species, and the extent of reaction. So if we're looking for our N1 is CH4, and that is going to be equal to what's going in, which is 0.5 times 100, so we have 50 moles. Since CH4 is in the reactant side, our extent of reaction 1 is going to be a negative in this reaction, for this equation, so negative 1. And CH4 is also in the second one right here, so we also have a negative C2. Yeah, I'm calling that C. So we have our first equation. Now we move on to the other equations. N2 for O2. O2 also has 50 moles going in, minus O2 is in the reactant side on our first equation, so minus C1. And O2 is also in the reactants on our second equation, so minus 2, because we have moles right here. So now we move on to N3. N3HCHO. For N3, we don't have any HCHO coming in, as you can see. So we don't have to put anything here. So we go to those RCs first. HCHO. It's on the product side. So our equation is going to look like this. C1, positive, because it's on the product. And that is the only one. So there's our equation for N3. N4. N4 is H2O. There's no H2O going in, so we look for H2O in our two reactions. Have one in the product side, so C1, and 2 right here on our second equations. So plus 2C2. Now, N5, CO2, we don't have anything going in, no CO2 going in. So we're going to go to the equations, and there's only one CO2 at C2. So our equation is just C2. Okay, so if our fractional conversion for methane is 0.9, we can write our equation for fractional conversion, which is going to be the amount of methane that we have going in minus the amount of methane going out, which is our N1, over the amount of methane going in. That is equal to 0.9. That is fractional conversion. And from that equation, we can easily solve for our N1. N1 is going to be equal to 5 moles. So we have 5 moles of CH4 per second. Now, we're also given the fractional yield of our formaldehyde. So fractional yield of HCHO is the ratio of HCHO formed to methane fed. So we're going to use the fractional yield of HCHO to calculate to calculate N3. So N3 over 50 moles fed of our methane is going to be equal to our given 0.855. That is the fractional yield of formaldehyde. And with that equation, we can easily calculate N3, which is going to be equal to 42.75 moles of HCHO per second. So now we have N3 and N1. Luckily, N3 is the same as C1. So we now have our C1 is equal to our N3, 42.75. And with that C1, we can calculate our first equation, because we also have N1. And that is going to look like this. N1 is equal to 5 moles. So 5 equals to 50 moles minus our C1, which we already have. So minus 42.75 minus C2. From there, we can solve for the C2, and that is going to give us a C2 equal to 2.25 moles per second. That is our C2 right here. And with this C1 and C2, we can just plug it in our equations and get N1 and N2, N4, and N5. Real easy. Now to find the composition of the output stream, we have to divide each one of our N's by the total product stream, which is going to be the total of our N's. And in this case, if you've already calculated, which I hope you did, you might have noticed that our N total is equal to 100. So let's calculate our composition for CH4, which is going to be equal to our N1 over our N total. And that is equal to N1, which is 5, over a total of 100. So our composition for this would be 0.05 moles of CH4 per mole. And you repeat that for every single one of the ones. Just divide your N by the total. So now we divide the molar flow rate of HCHO in the product stream to molar flow rate of CO2, N5. in order to obtain the selectivity of HCHO with respect to CO2. That will give us our selectivity of 19 moles of HCHO per moles of CO2. And that's it for this problem.